This is Kenji Fuji speaking. This time I would like to make a presentation entitled Nonlinear Seismic Response of a 7-story reinforced concrete condominium retrofitted with low yield strength steel damper columns. So let us start from introduction. The topic I would like to talk about is the seismic retrofit of existing RC condominium using damper columns. What I called damper column is shown here. In this column, a shear damper panel is installed in the middle of column. The shear panel damper, this red panel, is made of low yield strength steel plate. This absorbs seismic energy as cumulative strain energy. The concept of seismic retrofit of existing RC building using steel damper column is shown here. This is the existing concrete condominium. A new steel frame is added in the balcony side of the condominium. This is a shear panel damper. The problem I would like to discuss is how to evaluate the seismic response of a retrofitted building with damper column. What I'm showing to you is a stress-strain relationship of a shear panel damper. As you see, the strain hardening behavior of low yield strength steel is significant. In this figure, the shear stress is increasing more than twice of initial yielding stress. In the nonlinear dynamic analysis or time history analysis, strain hardening effect can be directly considered by using proper hysteresis rule. However, how to consider the strain hardening effect in the nonlinear static procedure? It is a problem I would like to talk about. In this presentation, a simplified procedure for predicting the peak response of a retrofitted building with a low yield strength steel damper panel considering the strain hardening behavior is proposed and discussed. So I would like to discuss about the seismic analysis method. As I talked, how to consider the strain handling behavior is the key of this presentation. In the nonlinear dynamic analysis, this can be directly considered by using proper hysteresis rule, such as IK model proposed by Professor Nakashima in 1995. However, in the nonlinear static analysis, this cannot be considered because the nonlinear static analysis is monotonic loading while the strain hardening behavior is occurred significantly in cyclic loading. So in the study, the use of two models is proposed for the prediction of peak response, the lower bound model and upper bound model. The predicted results from each model are enveloped for the final prediction. Here shows the building model used in this study. This is a 7-story steel reinforced concrete building designed according to PURE 1981 Seismic Design Code of Japan. In this presentation, only two models are shown. The one is Model 070, which is a model without additional frame, and the other is Model 07D0106, which is a model with additional frame on a balcony side. The damper column is installed on the first to 6 stories. In the study, connection of an additional steel frame to an existing RC structure is assumed to be rigid. Note that the seismic threat and additional shear reinforcement are assumed to be properly provided to the existing column in frame Y1 to prevent shear failure. Here shows the hysteresis rule for nonlinear dynamic analysis. In RC members, shear failure is not considered and the behavior of all members are assumed in a ductile manner. Modified Muto model shown in A is used for the nonlinear flexural spring at each member end, and origin-oriented model shown in B is used for the nonlinear shear spring of columns with wing wall in frame Y0. In damper column, IK model proposed by Professor Nakashima, shown in C, is used for the nonlinear shear spring. This model can consider the strain hardening behavior due to cyclic loading. Note that the flexural behavior of damper column and beams in additional steel frame is assumed to be elastic behavior. Here shows the pseudo acceleration response spectrum. In the study, two groups of artificial ground motions with the same target response spectrum are considered. The one group is at L, the other is at S. Note that the difference of two groups is duration, which may affect to the strain hardening effect. In this analysis, 12 artificial ground motions are generated in each group. This figure shows the prediction of peak equivalent displacement. As you see, the predicted peak response of model building is effectively reduced by the addition of dampers as expected. From the comparison of model 07O and model 07D0106, the reduction of equivalent displacement is approximately 40% by addition of dampers. This figure also shows that the difference of equivalent displacement between low bound model and upper bound model is small, although the equivalent acceleration of upper bound model is notably larger than lower bound model. Here shows the comparison of peak response drift obtained from the time history analysis and simplified procedure. As you see, in model 07O, the predicted peak drift is close to the mean of the peak drift of the at L series, while the mean of the peak drift for at S series exceeds the predicted peak drift. While in model 07D0106, the mean of peak drift for at L series is larger than that of at S series. The predicted peak drift, which is obtained as a result of the envelope of lower bound model and upper bound models, agrees well to the mean of time history analysis results. Here shows the comparison of deformation and shear force of dampers. As you see, the predicted damper deformation and forces are conservative compared to the time history analysis results. According to the difference of damper force due to the different duration, the mean of peak shear force obtained for the at L series is larger than that obtained for the at S series, as expected. However, the difference is not significant. Note that the predicted damper deformation is determined from the results of the lower bound model, while the predicted peak shear force is determined from the results of upper bound model. So the use of two models for the prediction is reasonable. In this presentation, a simplified procedure for predicting the peak response of a reinforced concrete buildings with a low yield strength steel damper panel considering the strain hardening behavior is proposed and discussed. In the study, the strain hardening behavior is considered by the use of two models to predict the peak response. The proposed procedure can satisfactorily estimate the peak response of a retrofitted building with damper columns considering the strain hardening effect. This is the end of my presentation. Thank you very much.